All right, so this lesson is going to be on simple machines, and it's going to be a little intense. We're going to kind of hit up all of the rest of the information that we need for this particular unit. All right, so a machine is an instrument which is going to make work easier, and we've already looked at work and defined work as the relationship between the force and the distance that object is moved. So we can look at work in terms of work input, and this is going to be the amount of work which is put into a machine. And this is provided by the force applied, which we call the effort force. And we have work output, and this is the amount of work done by the machine. And it is used to overcome the force that you and the machine are working against, which we call the resistance force. And resistance for its force is the weight, which is FW, weight. So weight, and remember weight is going to be, if we look at our reference tables, you can remember here that we find FG right here. That is weight. That is weight, okay? And Fg is the mass of an object times gravity. Okay, so that is the weight of the object which is being moved. All right, so we can look at work in terms of conservation. So machines are going to help work be conserved. All right, the greater the force produced, the shorter the distance. And the less force produced, the longer the distance. All right, so work output is less than work input because work will be lost due to friction. All right, and we spent a lot of time looking and working on friction last unit and even in this unit as well. All right, so friction will always cause there to be less work that is put out than what is put in. So we're going to look at our types of simple machines, and then we're going to come back and look at efficiency and mechanical advantage. All right, so simple machines do help us do work more easily. They do not save work from being done. They just help it be done more easily. So a machine can make the force that we put into an object greater. For example, pliers. A machine can change the direction of the force. For example, a car jack. All right, if you've ever had a flat tire, you may have had to use a car jack. A machine can increase the speed of the force. For example, a bicycle. Okay, simple machines have mechanical energy. That's the energy of motion. Energy output compared to energy input is going to be called its efficiency, and we're going to look at this in a little bit more detail once we talk about our types of simple machines. There's some examples of mechanical energy: wind, moving rocks, and waterfalls. So basically, if it has movement, it has mechanical energy. All right, so we have 6 main types of simple machines. Okay, so let's look at these 6 main types. The first one we're going to look at is going to be an inclined plane. Inclined planes are going to require less force. However, objects have to move a greater distance. All right, so for example, a ramp. A lower the slant, the greater the distance, okay? So the lower the slant, the greater the distance. The lower the slant, the greater the mechanical advantage. So there's a specific moving company that advertises that their moving trucks are the easiest to load and unload, and they even show a picture on the back, distance of our ramp, right? And it's got a back, and they're like, here's our ramp distance, and here's the other competitor's ramp distance higher, and they use that as an advertising tool. The reality is, by having this lower slant here, we are increasing the distance, but we're also increasing the mechanical advantage. All right. A screw is an inclined plane that is wrapped around a central bar or a cylinder, and it forms a spiral. So screws have a long distance, which causes their effort force to multiply. And the closer the threads, the longer the distance, but the greater the mechanical advantage. And if you've ever done any sort of home improvement projects, you may know that there's tons of different types of screws, and every project needs a different screw, okay? Because our threads are closer together, they're further apart. It really depends on what we're doing as to what kind of a screw that we need, okay? So how much mechanical advantage do we need? A wedge. A wedge is two inclined planes joined together, and they move. All right, so two inclined planes joined together that move. If it is long and thin, it has less effort force needed. All right, and a greater advantage. So some examples of a wedge would be an axe, a knife, zippers, and even locks and keys. All right, our next type is going to be a lever. So levers are going to have a rigid bar that pivots on a fixed point, which we call a fulcrum. A short resulting distance is going to equal a greater force, and a long resulting distance is going to equal less force to move the object. The mechanical advantage that takes into consideration both the force and the distance. Okay, so depending on what we're moving will depend on what kind of a lever we may want to choose. All right, so let's look at a first-class lever. A first-class lever is where we have a fulcrum. Remember that fixed pivot point, which is in the middle. The effort force, that force you put in, and the resistance force, called the load, are on opposite ends. The closer the resistance is to the fulcrum, the more the effort is multiplied. So let's look at a picture and see if we can't make this make more sense. All right, so over here, these pictures are not mine. I got these pictures off of the internet, so I have to give credit, all right, to the internet websites that I found for these pictures. Now, our fixed point here is the fulcrum in the center. All right, the effort force, that's what you put in. And then here is what we are moving, the object we are moving, so that is going to be our resistance force, if this is a first-class lever. All right, so the closer this resistance is to the fulcrum, all right, if we were to move it closer, the more our effort is multiplied, okay? So basically our effort gets multiplied. All right. When our fulcrum is midway between the effort and the load, there is no change in force, speed, or distance. So that's this first one right here. Okay. When the fulcrum is closer to the load than to the effort, there is a loss in speed and direction, but a gain in force. So we have a loss in speed and distance, but a gain in force, and that is our second one. When our fulcrum is closer to the effort force, there is a loss in force, but a gain in speed and distance. Crowbars and oars are examples here, and this third picture is that, what we just talked about, the movement of the fulcrum. So we can make a lever and we can adjust it depending on the needs that we have. All right, a second class lever. All right, so for a second class lever, this is when the fulcrum is on one end and the effort force is on the other end, and the resistance is in the middle, which you can see from my picture here. Again, this is not my picture. I cannot take credit for this picture. All right, borrowed it to use for educational purposes. All right, the closer the resistance is to the fulcrum, the more the effort is multiplied, and it's going to produce a gain in force, like a wheelbarrow, doors, nutcrackers, bottle openers. These are all examples of second class levers. All right, so we have our fulcrum on one end, our effort force on the other, and our resistance in the center. A third class is where the fulcrum is at one end, the resistance is at the other, and the effort force is in the middle. So in a third class lever, force is not multiplied, but the distance is multiplied. So I can get something to move longer. I usually see a loss in force, but a gain in both speed and direction. Shovels, hammers, tweezers, baseball bats, these are all examples. And here you can see from this picture, again, that I use for educational purposes. Our fulcrum is on one end, the resistance is on the center, but my effort force is, my resistance force and my fulcrum are on the ends. My effort force is in the center. All right, two more types of simple machines. We have pulleys. All right, pulleys are where we have a rope, belt, or chain wrapped around a grooved wheel. And this is going to change the direction of the force or the amount of force. And the direction changes assumes pulling down on a rope is easier than pulling up. So we're making the assumption here that it's easier to pull down than pulling up in order for our pulley. So we have three main types of pulleys. We have a fixed pulley. Fixed pulleys do not multiply. They simply change the direction or the distance pulled, okay? And this is going to equal to the distance being moved. So whatever I pull the rope, that's going to also be the same amount that the object moves. All right, so here's a picture which I borrowed, I found, and this is showing you your fixed pulley. All right, a fixed pulley is attached to something and it does not move at all, or whatever it's attached to is not moving, like a ceiling or the wall. Okay, so it's attached to something that doesn't move. It is a type of first-class lever with the fulcrum located at the axis, and it uses ropes or chains. So a movable pulley is going to be attached to an object. So the pulley is actually attached to the object, and it multiplies the effort and decreases the distance. So less effort's needed to get it moving because it multiplies the effort that I put in, but the distance an object moves will decrease. All right, so that's our second picture. All right, it is going to act as a second-class lever. And finally, we have compound pulleys. Okay, so a compound pulley is a system of movable pulleys called blocks and tackle. They have a greater mechanical advantage that can be obtained because each additional section or rope will increase the mechanical advantage. All right, so here is an example of a compound pulley, and you can see we have lots of different pulleys within it. All right, and finally, our final type of simple machine is a wheel and axle. This is a large circular object, which we call wheel, and that's going to move a smaller object, which we call the axle. Okay, so here's a wheel and an axle. The larger wheel is going to multiply the force of the axle there will be less effort force needed, so the amount of effort needed to put in is less on the larger wheel, producing a larger resulting force. And it will depend on the radius of the wheel compared to the radius of the axle. So there's our 6 types of simple machines. So let's go back. We have one more thing we need to go back and finish, and that is to talk about efficiency and mechanical advantage in a little bit more detail, because we've seen these words efficiency and mechanical advantage appear in our definitions of the simple machines. So let's look at them in just a small amount of detail. So efficiency is the work output, so what I get out, compared to the work input, what I put in. It can never be 100% because we saw earlier some energy is always lost as heat due to friction. But we can calculate the efficiency where we have work output divided by work input, and we're going to multiply it by 100 to make it into a percentage. So what is the efficiency of a machine that generates 3,400 joules of energy from 3,600 joules of a source? Okay. So what we get out is 3,400 joules. That's what the machine gives us out. What we put in is 3,600 joules. And we're going to multiply that by 100 to give us a percentage. So the efficiency of this machine is pretty efficient. It's 94.4% efficient when you plug that into your calculator. So how much energy is produced by a machine that uses 600 joules of energy at 65% efficiency? So in this case, I've been provided efficiency. All right, and I have to figure out my work output. So if I was to set up my equation from using my triangle, I'm just going to do WO for work output divided by WI for work input, and then E for efficiency. So it's asking me here how much energy is produced. All right, so that is the output. What am I getting out? So I'm going to take efficiency, which is 65%. Now, we multiplied up here by 100 to get our percentage. So I'm going to have to divide 65% by 100, and that gives me my efficiency is 0.65 times my work input, which is 600 joules. And when I plug that in, I get 390 joules. So that's what I would get out of the machine. The mechanical advantage is the number of times a machine multiplies the effort force, how much effort I put in. It tells us how much force is gained by using the machine, and it is the ratio of resistance. All right, the resistance force to the effort force. And our equation for this is going to be mechanical advantage, and this is going to be the resistance force divided by the effort force. And again, we're going to multiply that by 100.